Hey everybody, welcome to the first lecture for Contemporary Math, Math 131. Today we're going to be talking about inductive reasoning and deductive reasoning, the differences between them, and some of the minutiae when talking about these two different types of reasoning. So to start off with, let's talk about inductive reasoning. So inductive reasoning is this idea of taking and looking at really specific examples and coming up with a general conclusion about how all things behave in some sense of that term, right? So one of the downsides to this is that using inductive reasoning, we don't always necessarily arrive at a conclusion that's always true. It's because of this that we oftentimes call ideas that have been arrived at using inductive reasoning, we sometimes call those ideas conjectures. So, as an example of what this might look like, let's say we've got a set of numbers. 3, 5, 17, and 19. Now, all of these are prime numbers. Looking at these, it seems reasonable to make the conjecture that all prime numbers are odd. Okay. We arrived at this conjecture by saying, cool, we've got a set of numbers. 3, 5, 17, 19, a really specific set of numbers. And they're all prime, so it must be that all primes are odd. Hence our conjecture. Unfortunately, our conjecture is wrong, because the number 2 is also prime. So we could say 2, 3, 5, 17, 23, etc. And just grab a bunch of other primes and really quickly see, all right, cool, well, 2's inside of this, so since 2's even, our original conjecture can't be true. It must be the case that, except for 2, all primes are odd, which that is a true statement. So this is an example of just inductive reasoning on a whole. Let's next look at the differences between strong and weak inductive reasoning. So, this idea of strong inductive argument and weak inductive argument, the key difference between the two is going to be where we're pulling our samples out of to create our test with, right? So what I mean is, more specifically, the strong inductive argument is going to be the case of saying, I've got this bag of things, I'm not going to put any constraint on how I pick from this bag of things to create my test sample with. I'm just going to pick them out randomly. Quite literally what the definition is, right? We're going to randomly select from the population to create our test sample with. On the other case, with the weak inductive argument, we're going to say, I'm going to constrain that a little bit. I'm going to have this bag of things I'm pulling from. I'm only going to pull from a specific part of them. Maybe I only pull from the bottom of the bag, or I only pull from the top of the bag. This would be an example of that, right? More specifically, we're just saying that we're restricting our test sample to come out of an already made sample that's a part of the entire population. So let's look at two different examples of this. In the case of a strong inductive argument, we might have something like phone polling. Every election cycle, we all get those phone calls about, hey, who do you like? What do you like? How do you feel about this? How do you feel about that? Well, what they do there, assuming it's not a biased poll, what they do is they just say, here's a list of phone numbers from the entire US. We're going to randomly pick a handful of them and call them and poll them, get an idea of what their thoughts are. Using that same example, pretty clear if I randomly pick all the numbers from all across the US, it should be a strong inductive case. But if I say, let's only choose phone numbers that are from Montana, or Oregon, or Oklahoma, because Oklahoma, right? If we choose those numbers, then we don't have a strong inductive argument. Now we're saying we're only starting with a handful, which that's not necessarily going to be representative of the entire population. And this is the key idea between the two different types of inductive arguments. Strong is that idea of I want it to be randomly distributed amongst the entire population of what I'm testing. Weak is I don't really necessarily care. Maybe I want to bias a poll, or maybe I just am not even thinking about it, and I have, for whatever reason, a bunch of numbers from Illinois that I'm calling instead of from the rest of the nation. That would be an example of weak. Having said that, let's look at a couple of examples of inductive reasoning in general. So, as a couple examples of what inductive reasoning looks like. We've got these two sets of numbers here. We're going to look at predicting or answering these two questions here. Looking at this first set of numbers, some of you may already recognize it. It's a famous set of numbers. But we've got 1, 2, 3, 5, 8, 13, 21. We might notice going through it that okay, 1 and 1, whatever, but 2 is the sum of those previous two values. 3 is the sum of those previous two values. I can see a pattern. 13, the sum of the previous two patterns, or the previous two values. So if we wanted to answer this question, we might make the conjecture that the pattern here, what's happening, is that we're adding the previous two values to get the current value. So in this case, if we wanted to answer this question, what is the next value, using inductive reasoning, we might logically assume that it's going to be 13 plus 21. Okay? So we go ahead and put them together, 13 plus 21, it's going to come out to be 34. Now, like I started to say, you might recognize this set of numbers to begin with. It's because it's what's called the Fibonacci sequence. That was a tongue twister, and I don't know why. But it's called the Fibonacci sequence, and it's a really famous sequence because it shows up in nature and all over the place. And this is, in fact, the next value in that. All you're doing is you're adding the previous two terms to get the current term. So, again, 1 plus 1 gives you 2, 1 plus 2 gives you 3, 2 plus 3, 5, 3 plus 5, 8, so forth and so on. All right, cool. So let's look at this next set. This next set of numbers, 0, 1, 1, 0, 1, 1, 1, 1, looks like it might have something to do with binary already, right? Maybe. Except this next number is now 1, 2. Okay, so it can't be binary because we have 2. So what's going on? Well, let's keep looking at these numbers. So we go from 1, 2 to 2, 1, 2, 2, 2, 2, 2, 3, 3, 2. So what's happening here? What might the next four values be? Well, one pattern that I personally see here is we start off with 0, 1, and we flip the two digits, and we get 1, 0. Then we replace the 0 with 1 greater than it, we get 1, 1. And we flip 1, 1, we get 1, 1. Replace that trailing 1 with a 2, and we get 1, 2, so forth, so on. So we might logically assume that the next four values in this set of numbers would be something like 3, 3, 4, 4, 3, so forth and so on. So this is one reasonable inductive assumption, one reasonable inductive conjecture for what the next four values might be. Next, we're going to talk about deductive reasoning and what all goes into that and what it even means. So, the idea of deductive reasoning is to take a very specific statement and to prove conclusions about it using a more general version of that statement. When we do this, those conclusions that we prove to be correct, we call those theorems. So as an example of this, let's consider this case, this particular example, right? We're going to choose any random number, we're going to multiply it by 5, then we're going to take that product and add 10 to it, then we're going to divide that product or that sum by 5, then we're going to subtract 2 from that quotient. Let's go ahead and try a couple numbers. For kicks and giggles, let's start with 5. Actually, change that. Let's start with 1. It'll be a little bit easier. So, we've got 1 times 5. That's going to be equal to 5. Now we're going to add 10 to it. Okay. Now we're going to divide the two values. We're going to divide the sum by 5. Okay. So 15 divide 5, that's going to give us 3. And now we're going to subtract 2 from that. Okay? 3 minus 2 is going to give us 1. So in the case that we started with 1, our answer comes out to be 1. All right, let's try another value. This time, let's try 5. We start with 5, we multiply by 5, we're going to get 25. Then we're going to add 10 to it. That's going to give us 35. Now we're going to divide by 5. 35 over 5. That's going to give us 7. And now we're going to subtract 2 from it. We're going to end up with 5. So we put in 5 and we got out 5 this time. Let's do this with one more value. This time, let's put in 3, just because. So, start off with 3, multiply by 5, we're going to get 15. We're going to add 10, that's going to give us 25. We're going to divide now by 5. That's going to give us 5. And now we're going to subtract 2. And we're going to get 3 back. All right, so we've tried a couple specific examples. I think I see a pattern. Whatever we put in, we're going to get back out. How can we prove that? How can we generalize this statement to prove it? That's the question, right? Well, we can start by saying, let's let any number, whatever number we choose, let's use a dummy variable, a dummy value. Just call it n, just because we can. All right, we're going to call this n. So first step, we want to multiply n by 5. Okay. Next step, we're going to want to add 10 to it. The next step, we're going to want to divide by 5. And for our final step, we're going to subtract 2. All right. Looking at this, it may not be obvious right away how we're going to use this to prove our conclusion. The way we're going to do it, we're going to use just simple algebra. And we're going to break up this fraction into 2 parts, reduce it. When we reduce it, we're eventually going to get rid of this negative 2. We're going to show that our conclusion's right. So let's do that. Breaking this up, we get n times 5 over 5 plus 10 over 5 minus 2, which gives us n plus 2 minus 2, which gives us just n. So, using deductive reasoning, we said, let's take our conclusion and let's prove it by generalizing the statement. We have a pretty specific statement. We put in a number, we get out a result. We think we can generalize that result. And here, we go through the process of actually proving our conclusion. So our statement's a theorem now. We have this theorem that this will always be equal to n. And it is. And that is, I think that is all I've got for y'all on this. If y'all have any questions, by all means, feel free to shoot me an email. I'll be happy to help. In the meantime, have a good one, guys.